Okay, I guess last week we stopped at this point. Types of input-output. We said that there are two ways of issuing instructions about the input-output. One of them uses memory mapped I/O. The other one uses the separate input-output and memory space. This is a separate input-output and memory space. So you have actually two address spaces. One is for the input-output ports. The other one is for the. Let me get this. And this. The other one is for the input-output. The other one is for the input-output again. So their instructions are different. We use our regular instructions to access the memory locations, like loading a register from a memory location or writing to a memory location from a register. But for the I/O ports, we have other sets of input-output instructions. Very simple input-output instructions, actually. Not direct, indirect accessing kind of stuff. It is simple in and out instructions, just two of them. It is this type. When you have the memory mapped I/O, your I/O space is exactly the same as your regular memory space, memory address space. It's the same thing. So that's why you can use your all types of memory access instructions to access the I/O registers. Remember, these I/O registers are. Remember the picture? Okay. Each controller has some kind of a memory in them, some register in them, okay? And they have their addresses. So we need to write to these addresses, and you need to read from these addresses. So how do we do that? Without doing this, I cannot communicate with the keyboard or the printer, okay? If I like to send a character to the printer, I need to write to this special register here, okay? So when we do the memory mapped I/O, the hardware, okay, our system hardware says that, okay, this address is for the printer, okay, and this address is for the, for example, USB stuff, etc. So this is the memory mapped I/O. So when you try to read from these addresses or write to those addresses, you are actually modifying those registers in your controller cards. But for the I/O ports, this address space is different. Again, you are bringing those stuff. From the memory address space to this address space. We talked about those. And mostly our modern CPUs, our modern computers, they use this scheme. It's kind of hybrid. You can use both of them. Okay, you can use both stuff, either the memory address or the I/O space. And I think last time we talked about the advantages of both, the advantages and disadvantages of both of them. Okay, memory mapped I/O, we like it because you don't need any special instructions. Everything is nice. Okay, and with memory mapped I/O, no special protection mechanism is needed, because when you say this page is a special page, then you make it protected and etc. But with the memory mapped I/O, we had this problem. Remember this problem? Okay, maybe I should just delete those. Yeah. What was the problem with the memory mapped I/O? We talked about this last time.
Not cacheable.
What?
Not cacheable.
Oh, not cacheable. Well, caching is a problem, definitely, yes. I mean, what you mean is, since we think that I/O address space is part of the memory address space, and between memory and the CPU there is a cache. There should be a cache for the performance reasons. Then we should be careful about that. Yeah. But I mean, I'm talking about this picture. What did this picture say? They say that there is a problem with the memory mapped I/O because of the bus structure.
Too slow.
What?
It will be too slow since it's not writing to the register.
Too slow to write to where?
To the register.
Memory mapped I/O is slow? Why? You're kind of close, but it is not exactly slow.
You need, here there is an additional bus if you want it fast write, I assume.
Usually, I mean, this is the simple bus structure that I show you, that I keep showing you. But this is not a realistic bus structure. We don't use this kind of a bus structure. Because if this kind of a bus structure, as you say, is slow, instead we have this kind of a bus structure. There is a direct bus between CPU and the memory, right? So this bus is much faster than the regular system bus. So what does this have anything to do with the memory map I/O? The thing is this: since we are accessing our I/O drivers, okay, I/O controllers using the memory I/O memory address space, there should be one kind of a mechanism that says that whenever I try to write to this memory location, it is actually not the memory but the I/O. So your memory control unit, memory management unit is going to be more complicated. It is going to be more complicated because that unit has to decide that instruction is accessing a memory location or I/O controller device. Okay, so implementing this in the I/O space, actually memory mapped I/O, is more difficult than implementing the I/O space. Okay, so maybe I should back up a little bit and go to the beginning of the chapter and try to remember what we were doing. Okay, three things. We are looking at these principles of I/O hardware. Okay, these are the things about the these are the minimum of the things that we need to look at about the I/O hardware. Then we are going to look at the principles of software, I/O software. Okay, what we are doing with the software, the concepts about the software for the I/O. Then we are going to look at the I/O devices one by one. We are still doing the hardware. Okay, so to access the I/O controllers, registers, this is what we need to do. That's what we set up to now. So let's look at another hardware concept, which is direct memory access. We heard about this direct memory access. We kept talking about this. It's a hardware thing, but we need to be familiar with this concept, DMA. So the thing is this: whenever we ask for data from a I/O device, okay, the I/O device makes the data ready, and usually it is okay. Let me go back to my favorite picture again. Let me use this one. Okay, operating system asks one of the I/O controllers to load some data from somewhere, and the I/O device says that, causes an interrupt, and it says that, okay, your data is ready. As you ask, it is 2 kilobytes of data. It's ready. Okay. Now the operating system knows that my data is ready inside this controller's buffer. So using those I/O instructions or the memory mapped I/O, I need to transfer these bytes one by one to the memory. Who is going to do this? Of course, the CPU is going to do it. But CPU is something very valuable for doing this kind of a straightforward, stupid stuff. Okay? Maybe I shouldn't waste my CPU time doing something very, very straightforward. It is just a simple loop. It says that copy all those bytes from one address to another one. You might say that, well, I do this many times. I do this many times. What am I gonna do? I mean, this is just something that we do, but I mean, this is something very common and nothing will change about this operation. So maybe I can speed this up using some kind of a hardware structure. That's why we say that we have DMA, direct memory access. Okay, so the direct memory access says that why don't I have a new device, okay, new device that sits on top of the system bus, and it handles these kind of copying stuff from the main memory to the I/O controllers, or just the opposite way, from I/O controllers to the main memory. Okay, that's called the direct memory access. It has several registers in it. It's like an I/O device itself. You can program it. Okay, you tell the direct memory access device that you are going to copy, okay, this many bytes from this location to this location. Okay, and whenever the data is ready, direct memory access does that automatically. So it is basically a very simple CPU, very simple CPU. All it does, it doesn't do any arithmetic stuff, of course. All it does is copying data back and forth between the main memory and the I/O controllers. Okay, that's what the direct memory access device does. Again, it is like an I/O device itself. It can be programmed. It has its own registers, and you put your data in these registers, and that's how you program this DMA device. Without the DMA devices, okay, of course you have to do everything yourself. Okay, without the DMA, for example, for the disk, okay, this controller reads the block from the drive one by one, okay, and it puts that data into the controller's buffer, and then it calls an interrupt saying that CPU, the data is ready, and that interrupt is handled by the operating system, and operating system runs a routine that copies those bytes one by one from the controller's memory to the main memory. So that's what we do with without the DMA. With the DMA, this is the picture. Okay, let's see the picture here. Okay, let's see the picture here. The picture is CPU. Okay, CPU tells the DMA. Okay, see, this is like this is our main memory. This is the CPU. This is our disk controller, and this is our DMA device. As I said, it is like a I/O device. Okay, so with the DMA controller, first the CPU asks the disk controller to load that data to the from the drive. Okay, it asks that, okay, load this block from the desk. Okay, and then it programs the DMA controller. It says that, okay, when the data is ready, you are going to copy that data to this address, and this is the size of the data, that many bytes or that many words. Okay, some other control registers. Okay, and the DMA, whenever the data is ready, DMA, it just does that. It says that DMA requests a transfer to memory, and then the data is transferred by the DMA. DMA reads this data from that location, and it transfers it to the main memory location. When the data copying is ready, DMA calls an interrupt to the CPU saying that now data is ready. Okay, and of course that interrupt will be handled by the operating system, and operating system knows that now the data is ready in the main memory. Whoever asks for it can be notified about the situation. Okay, so the CPU does a little thing. It just asks the controller to load the data, tells the DMA where to load that data, and after that CPU continues with whatever it needs to do. Doesn't do any real copying. doesn't do any real copying, and it gets just one interrupt. Okay, it gets just one interrupt when the data is ready. It doesn't do any copying from the controller's buffers. Okay, that's how the DMA. That's how useful DMA is, and then you might say that, well, I mean, since DMA will be, I mean, we talked about this just this controller here, but what if I have more than one disks? What if, well, I have many devices here, right? I mean, I just don't have a single device like the disk. I have the printers, I have the network device, I have the keyboard stuff and everything, I have the screen. So there are many things happening at the same time. That's why these DMAs are actually very capable devices. They can handle 16 DMA requests at the same time. Okay, they can handle 16 requests at the same time. So your DMA controller might be copying the data between many devices and the main memory for multiple devices, as I said before. Okay, good. Any questions? Well, as I said, this is a hardware thing. Why are we talking about this? Well, I mean, the programming this DMA is a software thing, and it's an operating system's task. Okay. Other than that, the rest of them is a hardware process. Okay. Any questions? Yes.
During the writing to the main memory, can CPU access the main memory? Because it is idle, you know, we are writing to the main memory.
Well, I mean, this is a bus, system bus, and only one device can use the system bus at the same time. Either your DMA is going to use it or the CPU is going to use it.
So where is the benefit of having DMA in that case? Because we are going to lose the same time.
Yeah. Well, that's a very good question, right? I mean, the question is this. I mean, I am not spending any CPU time to read data from the memory and the controller. Since the system bus is a bottleneck here, I mean, system bus becomes a bottleneck. Either the DMA uses or the CPU uses it. What is the use of the DMA for now? Anybody has any answers for this? I mean, what does the CPU do if it is not using the memory? Why does DMA? Why the DMA transfers all that data to the main memory?
Can use its cache for some process and do some computation.
Yeah, CPU usually 80%, 90% of the time, because of the principle of locality, it deals with the cache. Okay, so it works on the cache. That's one thing. The other thing is that you can optimize this picture again. Okay, DMA might have another bus between the main memory and the DMA. That could be another optimization, and your main memory may be divided into different chunks and etc. There are certain optimization, but the problem that you are talking about is definitely a problem. Yeah, that's. I mean, something has to be a bottleneck. I mean, we cannot think whatever the CPU does. We cannot think whatever the CPU does different, separate from whatever the DMA does, because both of them needs the main memory. Both of them needs this bus. But usually it is this. Wherever this DMA is transferring the data, okay, is different from the data that the CPU needs, because CPU already did the context switch. It is working on some kind of other process. That process uses a different part of the memory, and that memory is, when you do the context switching, is already brought up in the cache. Okay, so usually they can do these kind of optimizations. Okay, I mean, they are all connected to each other. If you think that one solution is going to do wonders for you, usually it is useful, but most of the time you will have those kind of conflicts. Remember, the fact that we have 8 CPUs nowadays, CPU cores on our computers, doesn't mean that our computers are 8 times faster, right? I mean, being 8 times faster is the absolute limit. You cannot be more than 8 times faster, and you would be lucky if you are 6 times or 4 times faster on the average, because most of the time you won't have any tasks to run 8 of them at the same time. Most of the time they will need the same memory part, and there will be race conditions, and you need to address those kind of problems. Yeah, I mean, this is the case. Using the DMA controller doesn't mean that the CPU is not going to do this data transferring at all, and this will come all free. No, it is not, but it will be better than CPU. Most of the time it will be better than CPU transferring all that data. Okay, good. Let me move on then. Let's talk back. Let's go back to this interrupt stuff again. Let me clear this out, whatever I have written before. Okay, so remember the interrupts. Like the DMA controller, I have the interrupt controller sitting on the system bus. Okay, and this interrupt controller, as we know from our hardware courses, it is responsible for getting the interrupt information from the I/O devices, okay, and then issuing an interrupt to the CPU. And when the CPU gets the interrupt signal, this one gives the information about the interrupt happened. Okay, this one says that there is remember the CPU cycle, it executes something. It just fetches the codes and executes, and in the meanwhile it checks if there is an interrupt. If there is an interrupt, then it has to stop whatever it is doing and it has to run a special interrupt handling procedure, and most of the beginning of that is handled by the hardware and the assembly routines. Then after that, our software, operating system software, interrupt handling routines takes over. And let's look at this process more carefully now. Okay. Okay, so this is kind of in summary. We kind of said these steps. When the I/O device finished the work, for example, your SSD device, for example, loading some data, it says that okay, I am done loading the data. Let's forget about the DMA for now. I have loaded this block for you. It is in my controller's buffer. Okay, it immediately causes an interrupt by asserting a signal on a bus line. Okay, and this signal is detected by the interrupt controller. So this I/O device, our desk, is causing this signal. This signal is detected by interrupt controller. Okay, the controller, okay, now has to communicate with the controller has to communicate with the CPU, saying that an interrupt happened and the types of the interrupt. Okay, puts a number on the address line specifying which device wants their attention, and once the CPU knows this information, it looks up the interrupt number. Okay, and usually it's a vector, interrupt vector. Okay, so our operating system keeps an interrupt vector like this, interrupt number 1, 2, 3, 4, 5, 6, whatever. Okay, so once the CPU knows the interrupt number, so it has a special routine for handling these kind of interrupts. Okay, so it starts running that one. So what is the function of this device here, the controller here, the interrupt controller? It needs to get all these interrupt signals, and it has to inform about the interrupt. It has to inform the CPU about the interrupt. There might be more than one interrupt happening at the same time. For example, let's say your disk and your keyboard at the same time said that the data is ready. Okay, this interrupt controller has to prioritize these signals. Has to say that, okay, I cannot wait. I cannot make the disk stuff wait longer than keyboard. So disk interrupts has more priority than the keyboard interrupts. So I am going to tell the CPU that a disk interrupt happened before I tell it that the keyboard interrupt happened. Prioritization and the conflicts and that kind of stuff, acknowledgements. So interrupt controller is something again complicated like the DMA. Okay, and this interrupt controller of course has to be programmed by the CPU, like the CPU programming the DMA. And of course, needless to say, both of these devices are special. Our end users, they don't have the privilege to access the interrupt controllers or the DMA controllers. Okay, these are all kernel stuff. Okay, the end user doesn't know anything about the interrupt controllers or the DMA controllers. Okay, so these are the things that had happened. Once the operating system knows about the interrupt type of the interrupt, okay, the operating system running its part, it says the interrupt controller that, okay, I got the interrupt, I am handling it, so the interrupt controller can now handle the other types of interrupt. And the hardware automatically, again, we talked about this, saves certain information before starting the service procedure, and everything we know about that just continues. So I didn't say many things new about this, but we just looked at this handling of the interrupts like an I/O device. Okay, so interrupt control is like a device. As the name implies, it's just controller. Remember this. This is the DMA controller, and if I go to our original bus stuff, okay. Video controller, keyboard controller, we said that these all have registers and that kind of stuff. And again, we have the interrupt controller connected to the system bus, and we have the DMA controller connected to the system bus. Those are controllers, and they have their own registers to modify. Again, using either I/O mapped instructions or memory mapped instructions or the I/O space instructions. We program them. Programming them requires privileges, kernel privileges. Okay, just this is what we said about the handling of the interrupts now. Okay, good. One thing that the hardware has a problem with, or needs to be careful, and we get our fair share of this difficulty from our operating system side, is this concept of precise versus imprecise interrupt. I mean, so far we talked about interrupts like, okay, I execute an instruction. After execution of the instruction, okay, after executions of the instructions, we check if there is an interrupt. If there is an interrupt, then I handle it. That's how I talked about it. But in reality, it doesn't happen that way, because we have this pipeline structure in our computers. Okay, we cannot avoid it. This is a very efficient way of executing instruction. We fetch, this is the simplest one, right? We fetch it, we decode it, and we execute it. So usually at the same time, there are 3 instructions are being executed. When the interrupt happens, okay, 2 of the instructions, okay, are not executed fully. This is the simplest case. If you have a superscalar CPU like this, more than one instruction execution path like this, and more than one execution unit, okay, the things are more complicated. That means what? For this picture, I have 7 instructions being dealt with. So they all have their different stages of the execution. When the interrupt happens, I have to stop, right? I have to stop and I have to handle the interrupt. So what is my decision now? Should I wait until all the instructions are executed? Okay. Or should I immediately stop whatever I am doing and go handle the interrupt and come back? Okay. Obviously, the first one is simpler approach. Wait until all the pipeline is cleared out. That's one solution. Wait for it. For this one, I need to wait for 3 cycles. Well, maybe 3 cycles is not that long. Is not that long to handle the interrupt. Maybe I can afford it. But if you have a super scalar CPU like this, it's going to be costly in terms of interrupt handling wait time. So what am I going to do? The other thing is this: if I need to wait until everything is cleared out, I am losing time, because after I handle the interrupt, I need to fill in all these pipeline stages again. Well, I know that handling interrupt is something expensive, and this will make it more expensive. Okay, so they say that we have 2 ways of handling it. Either wait until everything is cleared out. That's called the precise interrupt. Okay, and precise interrupts are shown that way. When you are handling the interrupts, you know that I have executed all these instructions at these lines. Okay, and I handled all the instructions before 3:16. After 3:16, I did not execute anything. I know that everything is clear. Okay, but for the other one, for the imprecise, I am lecturing here. Did you? So when you look at the right side of the picture, you see that when you are handling the instructions, I know that this one is not executed and this one is fully executed, and the rest of them are kind of, this one is only 10% executed, 40%, 35%, and it changes. This is a more efficient way of handling the interrupts. Why? Because I am not wasting any execution time. I am not waiting for everything to clear out. When I start again, I don't have to fill in all the buffers again. That's the good news about the efficiency. But the bad news is handling this kind of a interrupt picture is very difficult. Okay, because especially for the CSE machines, complex instruction set machines, there are many instruction types, and I need to save the state of the instruction somewhere, saying that this is like at the 3rd stage of the execution of the stuff, and their dependencies, hazard conditions, and etc. That's not going to be that easy, this with imprecise interrupts. So again, it comes to a trade-off stuff. And with the precise interrupt, everything is easy, but you know the problems. When the interrupt happens, the PC is saved in a known place. All the instructions before that pointed to the PC have fully executed. No instruction beyond that PC has been executed. I know that. So even if you have the super scalar pipelining, you have to wait until before the PC everything is executed. After the PC nothing is executed. We know that, okay? And sometimes we can do this. If an instruction is halfway through executed, maybe I can undo whatever it did, okay? Sometimes I wait, sometimes I do undo. Both of them are inefficient, because when you do the undo, you are wasting the whatever you did before. When you are waiting, you are wasting your CPU time. With the imprecise interrupt, okay, that's the problem. When the imprecise interrupt happens, CPU, okay, transfers all that kind of complicated information to some kind of a special stack, okay, special stack, and that stack holds everything about your CPU state, and your code, operating system code, is responsible from figuring out what happened what was happening when the interrupt occurred. Okay, so saving a large amount of information to memory on every interrupt makes your interrupt handling slow. Remember, interrupt means that you are going to context switch, right? Context switching is expensive, and this imprecise interrupt makes it more expensive. Okay? And so we need to be very careful about these handling of the interrupts, and we don't like, without the interrupts we can't do, okay? What is the alternative for the interrupts? Is polling. Polling is way more inefficient than interrupts, okay? But interrupts are not that efficient. You need to switch context, you need to invalidate your cache, you need to switch your memory management unit MMU tables, page tables, and etc. You remember all that stuff. It is expensive. On top of it, you have this imprecise interrupt handling stuff, handling all that kind of CPU data. It's going to be difficult. Okay. So concept-wise, again, you might say that why are we talking about the interrupts? We are trying to study operating systems, and interrupts are a thing of the hardware. Yeah, that's true, but as in the case of imprecise interrupts, you need, as an operating system designer, expert, you need to handle the state of the CPU when either save it and restore it when the interrupts happen. Okay? Any questions so far? Where is my attendance sheet? Okay, let's do this regular check. Ahmet Tuğkan, Hatice Sevra. Hatice orada mısın? Necdet Alaslan. Necdet. Yeşim. Yunus Emre. Yunus Emre. Yunus Emre Yumuşak. Hangisi, sen misin Yunus Emre? Yunus Emre Yumuşak nerede arkadaşlar? Yunus Emre Yumuşak. Sen misin Yunus Emre? Sen kimsin? Efendim? Niye elini kaldırdın? Adın ne senin? Bir tane daha Yunus Emre vardı. O Yunus Emre Geyik, Yunus Emre Öztürk. O nerede? Sen niye konuşmuyorsun bugün? Tamam. Okay, any questions? So this is all about that we are going to talk the hardware. Okay. After that we are going to talk about the software now. These are just the concepts, okay? Concepts that we need to be aware of when we are dealing with the I/O in terms of software handling. After that, we are going to look at the software part of the I/O. Okay, let me continue. Ya arkadaşlar, ya şu telefonlarınızı oynamayın ya. Şu arkadaş, sen şu şapkanı geriye doğru çevir, tamam mı? Heh. Şapkanı da geriye doğru çevir. Şapkanı. Heh. Şapka var ya, şu kafandaki şey. Telefonda eline al, bilmiyorum ya. Görüyorum ya. Bakmak istemiyorum, gözüm takılıyor, anlıyor musun? O köşe, özellikle köşe sizden çok şüpheleniyor. Gözüm oraya takılıyor. Ben de hep oraya oturdum küçükken. Orada güvende olduğunu sanıyorsunuz ama değilsiniz. Okay, principles of software, goals of the I/O software. So we are going to look at a few concepts about the software, like the device independence, naming. Let me go. Okay, synchronous software, buffering, and etc. And that will be about our discussion of software. Now we need to know about this stuff because they are all related to I/O. Okay, so one thing that we try to achieve in our in our operating system, I/O handling is the device independence. Remember the two things that we are trying to achieve with the operating systems. We said that we are trying to manage the underlying hardware. We try to abstract away the details of it. Okay, abstract away the details of the underlying hardware. Without doing the device independence, okay, without achieving this device independence, we can't do the abstraction. What do we mean by device independence? When I remember when you learned about the programming, C programming language, when you issue this function, okay, when you run this function, when you call this function open, it opens a file, okay? And we don't care where the file is. It might be on our SSD device, it might be on our mechanical disk or the USB device, or it could be a network drive. Doesn't matter where it is. I just open it, or I just close it, or I just seek some certain address of it. Doesn't matter. That's called device independence. So as an end user, as a user of the operating system, I don't care about the device that I am working with. As long as it's a block device, I just use this POSIX system calls, and it's going to work. Okay, so that's called device independence, and we should satisfy this constraint with our I/O. Okay, another one, maybe it is related to device independence, as the uniform naming. Okay, it should not matter again, like the device independence, where my file is. Okay, it is either a name, just a single string, or just an integer. Okay, that's my name for the file. Okay, doesn't matter where the file is. It could be on an SSD or mechanical disk or the USB. It should be uniformly named. So remember, for the Unix devices, for the Unix operating systems, we have the root directory. Under the root directory, I have the user directory, or the devices directory, or the libraries directory, and etc. Doesn't matter where my file is. I use this path structure and I find my file. And if I have, let's say, this is the mounting directory, right? M and T. I can mount my USB device here, SSD device here, and our other devices here. For example, the disk devices, mechanical disk devices. Doesn't matter, as long as I follow these paths, I can find any file that I like. I mean, the naming of the files are no different for each different type. Remember the second type of extensions for our CD-ROM devices? They say that they added these extensions so that the naming of the files is compatible with the Unix file system. It is that those extensions are just for this, okay, constraint uniform naming, so that I can have long file names with my devices. The same thing with the errors. Okay, with the I/O there can be lots of errors. Okay, the file I am trying to reach is not available, is not writable. I don't have any space on my device. There is a mechanical problem, I am not writing it. There is an electronic problem, I am not writing it. The sector that I am trying to write to is a bad sector, and etc. There could be, I don't have these kind of problems with my memory. I mean, my memory will not say that I am broken, you cannot write to me, or wait for me until I calibrate, and etc. But these kind of problems happens when you are dealing with the files. Okay, when you are dealing with the files, so I have to handle the errors, and this error handling has to be done by the I/O software. Error recovery, most of the time when it happens, it should be handled by the operating system. Okay, it should be done transparently at the low level without the upper levels even knowing about the error. So these are the kind of things that we are going to look at when we say goals of the I/O software, the second part of the chapter. Okay, and I will keep introducing these kind of concepts when we talk about the I/O software. Maybe the first concept that we are going to look at today is about the software is the blocking or interrupt driven transfers. Okay, when you transfer your data from forget about the DMA. Okay, when you're transferring your data between the main memory and the device controller, you either do a synchronous transfer or the asynchronous transfer. Okay, or sometimes we call this blocking. Sometimes this is called interrupt driven. The name is kind of a confusing name, but once you understand the concept, it is not that difficult. Okay, so most physical I/O is asynchronous. Okay, what does that mean? The CPU starts the transfer and goes off to do something else until the interrupt arrives. Okay, so that's called asynchronous. You don't wait until you don't go idle until your data is ready. Okay, you start your I/O and you go do something else. Whenever the I/O is done, okay, you will get an interrupt. Okay, that's called asynchronous or interrupt-driven transfer. Okay, so the other thing is the blocking one. You say that I need this data, and I'm waiting until the data is ready. Okay, so of course we like this one. Interrupts are way more efficient in terms of CPU times, but sometimes the synchronous ones, especially at the kernel level, is preferable. Okay. Any questions? And buffering is something that you always do when you are transferring data between the controllers and your main memory, and we are going to look at the types of the buffering in a few minutes. But before that, I need to take a break. If you have any questions. Okay, so let's be here at around 11:36. Kimdi o şeye derse gelen? Acelen ne senin ya?
Ben yanlışlıkla başkasının yerine
Dinleriz hani nerede?
kendi imzamı attığımda eski kotak
Ha, senin.
buraya attığımda
Tamam, bu arkadaş gelmedi değil mi? Faruk Ceylan yok değil mi burada? Nerede kalem versene, kalem. Kuşun oraya versene onu. Gelmez mi bu?
Hayır. Gelmez. Hocam buldum. Ezgi Korkan hocam bu arada.
Ezgi Korkan iyi, tamam.
Hocam ben 15 dakika geç kaldım ya.
15 dakika geç kalmak yok arkadaşlar. Bu sınıf birinci yoklama krizini tükettiği.
Hocam ben rapor almıştım da geçen hafta pazartesi salı için.
Dersten kalırsan bunu getir bize göster. Tamam. Kalmazsan problem yok. Tamam. Kaybetme onu. Evet.
Belki bana bağlı da.
Ha?
Üçüncü haber geldi.
Ha?
Orada link var işletim sistemi için.
Evet.
Çalışmıyor.
Ya onu ben Gizem'e söyleyeyim de bu belki özellikle bir değişiklik yapabilir. Kendi okumasını falan için. O linki de yapsın.
Benim aslında tek şey sadece şu kompliye de şu ikisini kompliye yaptıramıyorum. Bunlar obje diliyle kullanılıyor orada. Ama ben integer model yapmak istiyorum orada. Yaptırtamayız. Override yapman gerekiyor mu? Override yaptırım var. Onu çalışmak önemli. Bir de bu tabloda şeye göre vermiş ya, FK'ye, FD'ye. Ama bir çalışmazsa Çünkü şöyle bir şey var. Ben bunu şeyden aldım. Benim yapmak istediğim heap order'ı sağlamak, tamam mı? Offer metodundan aldım burada reheap'i. Şu while'ın içinde. Ama poll metodunda reheap'i de daha farklı yapmış mesela. Burada da bak keep list, property, restore konuşuyor. Offer bu olmaz. Kanka offer bir şey ekliyor, poll çekiyor. Ama poll minimum elemanı çekiyor. Buradaki reheap ile buradaki reheap farklı. Hoca demiş ki bize sadece, mesela soruda, sadece değişiklik yapacaksınız demiş, şurada set. Sonra da heap order property'yi sağlarsanız tam puan verir. Mesela şeyde, çözümleriniz komparator direkt compare diye bir fonksiyon yok. Compare to bir şey yapman gerekiyor. Kanka bu değil yani. Bunu ben eklemişim.
Bu arada eksici
VS Code niye mi? VS Code değil. IntelliJ'de de ben kodun ayarladım. Niye öyle bir şey yaptım? Link kullanıyorum. Ya şu an yaptım. Ha? İyi değiştirmiştim. Normal yap. İyi olsun. Neredeyse ya. Benim sınavın bir sayfasını görmedim. Ama orada hocam puan yani 5 falan. 3-5. Bir de Boğaziçi'nin bir yıl sözleşmeli dans hoculuğuna gitmiş. Seneye geçiyor değil. Boğaziçi'ne mi gidecek? Tatlı adam aslında. Ben Nermit'e sordum. Bir yıl bana dedi. Zaten şey yaptı. Ama Boğaziçi'ne gidecek. Gel çıkalım. Yoksa valla
böyle bir soru yok onlarla. Ben soruyu
Okanlar mı?
ben dönüşüm bulmuşum.
Çeyrekte yok ya.
En altta.
Evet.
Yani benim Data X ne yapar?
Dönüşüm de bilmiyorum ama ben göremedim. Dönüşüm yok. Dönüşüm buna bak. Eğer dönüşüm olsaydı, yani şu sol tarafın dönüşüm olsaydı, pardon, şey yapıyoruz. Dönüşüm yani buraya gelmiş. Aslında basit dönüşüm değil. Şey yok yani ama peki benim adımı okur muyuz? Ben de şaşırdım dedim bu sefer okur herhalde. Yine okumadı.
Karar verecek misin? Yani hepsini böyle toplayıp ortalaması.
Kişilerin ismini vermek lazım.
Ama o da aslında çok önemli.
Yok şey diye
Sürekli aynı bir
%100 şey
Bilgi ilerlerken değişiyor.
Tamam.
Yani aslında tam ortalaması almak da mantıklı olur ama her 10 saniyede bir mi ortalaması?
Şey. Tamam.
Çünkü mesela videonun için
Olabilir.
mesela
Şey istiyorum.
şey mesela şu bir tane kol var. İçine böyle yavaş yavaş yapıştığında bu. Yani aslında orada böyle tonlar yapıyor. Ama hani insanın moda girmesi için birazcık izlemesi gerekiyor. Bilmiyorum ama olur genel olarak geldi ama en başından sonra onu boğazdan alabileceğimiz sanmıştım. Ortalama olursa kullanmaz mı?
Herkes şu belki geliyor falan böyle.
Siz niye geliyorsunuz? Size çok garip bir olmuşsunuz. Kız şaka yapıyor, siz de gidiyorsunuz.
Peki videoda aslında
Haklı ama ya. Yok işte bunda şey yapmışlar var. Şu an sigara içiyorsun, sağlığı zararlısın var.
Bir de kalır atmalı. 10 saniye kalırsa 6 saniye.
Kızı da ağzına şakadan farklı korkutucu şakası var. Zaten bok içiyor. Sen de içiyorsun. Diyor ki yok bu Arapken. Birisi bana mesela böyle anlatsa tamam bak. Önümde bir işte Arapken nasıl öyle yapıştım. Ya siktirin.
bizimleri kaça böyle yollar gidiyor?
Ay kim de
Ne kadar
Çok kısa bir süre.
şakasından.
Ama yine 5'e bölünebilir olmuş. Yine 5'e bölünebilir.
Seninki gergin mi?
Ya ben de elle yüzeceğiz. Bu an geliyor şimdi ama tüm videoda hakim olması
Kim o ben değil. Şeyi hatırlıyorum. Belki hatırlıyorum.
Bizde olmuyor.
Anlaması zor da resetmesi daha kolay.
Ne?
Fotoğrafa baktığı sürece
Birisi
Tek bir şey öğretiyor.
bir değişim olmuyor. Şeye bakarak da sonra bak. Evet, şimdi onda değil mi?
çok kısa çok
Fazla da kapatıcı değil.
bir
7 tane sensör var. 7 sensör belki 3.'süyle 5.'si.
3 ay.
Birbiriyle korelasyon.
7 diye hatırlıyorum da daha 4
Bizde 4 var. Mesela şey 3.'süyle 5.'si sensörde bir şeyler alıyor.
Nasıl 6 saat?
Onlardan fazla işte ama.
Çok fazla. Sen
Elle yaparsın.
çıkmamışsın.
Ama bütün data parçacığını düşünsene. Bir videodan 10 tane çıkmış.
Benim de geldi.
Her bir data parçacığında 5 tane var. Bu ikisi birbirine çarpılacak. Birbiriyle ilişki kurmasını istiyorsan. Tek sensör olsa gerek kullanılabilir. Evet. Ya da 2 sensör olsa elle yapar. Ya da
Ama 6 saat nasıldır öpüyorsun? Çıkarken basmıyor. Bence bir şey yaptım.
değişim belki anlamak için 10 tane yeterli olmaz.
Tamam şey tutmak. Tutmak değil ya. Belli format.
Biraz sadece sevmiyorum.
Videoların süresi şey var.
Hayır bana adamlar bakıyorum.
Zaman aynı şey yani. Aynı sürede dedi. Bir de
Ama şey, bütün datayı düşününce korkuyla bağlanınca
O da var. Doğru.
Ya işte şöyle duyuyor. Şu an yani şöyle bir şey diyorlar.
Azıcık konuş ya.
Perşembe değil. Perşembe olmaz.
Gerçekten bir karşılığı olacak mı onların bir daha kiralı? Onu bilmiyorum. Onu ben de
Daha iyi.
Ayda 800.
Benim arkadaşım
Normal senin de
ofansız olan fikirler
So let's look at this sentence directly from the book. This synchronous blocking or asynchronous interrupt element I/O is this is the viewpoint of the operating system. Okay, as an operating system, when I am doing the I/O, I am doing it with the asynchronous interrupt element stuff, and this is how it works. But as the end user, I don't care about both of them, right? As the end user, what I'm saying is that when I say read, okay, from file number 2, this buffer 200 bytes and etc. Okay, as an end user, I don't deal with the interrupts. I don't deal with the blocking, unblocking stuff, right? But I know that as the operating system expert, when I say read, I will be blocked for maybe a few 100 milliseconds, and after the data is available, I will be unblocked and I will continue. I know this one, right? I am a programmer, but as an operating system expert, I know this. And this blocking sometimes is a problem for me. I don't want to be blocked. Okay, I don't want to be blocked. And some operating systems make this interrupt-driven, okay, asynchronous I/O available to the end users. Like an end user, I am saying that I am initiating an input-output operation. I am writing a program, and I know that I am not going to be blocked while the operating system is working on my I/O request. I will be doing something else. Okay, when the data is ready, operating system will let me know that my data is ready. Okay, so this is kind of a complicated picture for an end user, but some operating systems make this picture available for the end users too. Usually what we do is we just read the data. After we reading the data, we process the data. That's how we write our programs, right? So this is the way most of the operating systems are set up. But some operating systems say that, okay, I'm going to read it, but don't block me. Okay, I will go do something else. When the data is ready, call a function of mine, this function, and that function will be executed when the data is ready. So that's the meaning of this sentence. When you read the book, don't get confused about it. So let's talk about this buffering. Okay. So remember again. Let's look at this picture. Let's look at this picture. Actually, this picture, my favorite. Yeah. Okay. Good. So when it is about I/O, we talk about the buffers most of the time, and we need to know why we need the buffers. Okay, without the buffers, we cannot do I/O much. For example, let's say I like to do input/output without using any buffers. Instead of doing this picture, why don't I use the picture that comes from this one? Okay, so I am communicating with a modem. Okay, I am reading data from the modem or writing to the data to the modem. It doesn't matter what I am doing. If I am doing it character by character, okay, when the modem says that my data is ready, okay, one character, and I write that data to whoever asks for it to the buffers, and whenever the modem is ready again, I write data to the user space and wake up the user waiting for it. This is kind of input/output without using any buffers. Okay, and you might say that, well, this is okay. It might work to some extent, but it is very, very inefficient. Why? Because every time you get a new character, okay, you need to wake up the end user, this process, whatever it is, handle this character, I'm going to give you another character. This is too time consuming, okay? Because every time there is a new character, an interrupt is happening and you are switching between the kernel space and the user space and etc. This is not going to be very efficient. So that's why we say that the idea is, why don't we keep a buffer whenever the data is available? We put that the data to that buffer. When the buffer is full, after that we let the user know that the data is ready. Okay, so you buffer your data to some place, some temporary place, and you let the user know that the data is ready. Most of the I/O routines work this way, so that means that we have to buffer our data. Remember our cout statements from C++? When you say cout A, and this usually happens when you are debugging your code, right? When you say cout A, this A is not immediately printed on the screen, okay? Because our input-output routines are smart enough to buffer all these requests. When the buffer is full, the whole buffer is printed to the screen at the same time. Because for each character, if I am going to make a system call, that's the soft interrupt, kind of soft interrupt, okay? That's going to be expensive. So you wait until the whole buffer is full. After the buffer is full, you print it on the screen. This is much more efficient. If you like your data to be printed immediately, then you flush your buffer. You remember flush buffer? Flushing the buffers. Okay. When you flush your buffer, whatever you have in your buffer will not be held on. It will be printed immediately. So buffering is very useful. We will come to buffering, and okay, it simply means that storing your data temporarily at some place until the buffer is full. Okay, when the buffer is full, I can process all of them at the same time, saving our context switching and interrupt handling times for each character or for each data unit. Okay. So with the programmed I/O, this is kind of an example buffering scenario. Okay, in my user space, I am going to print these letters. Okay, when the buffer is full, I make a system call, and that system call copies all that buffer to my kernel space, and in my kernel space, either using programmed I/O. Programmed I/O means that printing the buffer characters one by one, or some DMA operation. I print the characters one by one. Okay, to the printer. To the printer. So maybe we should. I mean, maybe you knew this before. Maybe you should know it by now. So every time you make a cout statement, okay, cout A, B, whatever. Okay, that doesn't automatically mean it's a system call. Okay, our input-output libraries usually collect them as some kind of a buffer in our I/O libraries. When that buffer is full, there is a system call afterwards. Without buffer getting full, we don't make a system call. Okay. So. All this kind of stuff is done with the help of the buffers. Okay, let's see how this buffering is done with the programmed I/O and interrupt-driven I/O and DMA-based I/O. Okay, let's see all three of them. Remember, programmed I/O means that I am doing the input-output by the CPU one by one. Okay. CPU is dealing with everything. That's what we are doing. With the DMA, you just say that here is my buffer. Print this out for me. That's the DMA. With the interrupt-driven I/O, we will see. Okay, let's look at the programmed I/O first. I collected all of my data in a buffer, and I made a system call. This whole buffer is copied to my kernel space. Okay, and as an operating system, I am printing these characters one by one. How do you print a character to the printer? Again, printers have controllers, right? Controller devices. Inside the controller devices, there are special registers. I place this A into that special register, and I ask the printer to print that character for me, and it prints it. Whenever the character is printed, I get the new information from the printer, says that the printer is ready. I print another character and I print another character. This is called programmed I/O, and it's a very simple pseudocode for the programmed I/O. Okay, copy from the user buffer. Okay, I am going to copy user's buffer to my buffer, this many bytes, and in a while loop, from 0 to count. Okay, if the printer status register, okay, is not ready, then I am in an infinite loop, right? So the only way to exit from this loop is this printer status register becomes ready. Okay, when it is ready, then I am out of this loop. When I am out of this loop, I immediately put the character number I to the printer data register. So I have the addresses of two things. One is the printer data register. The other one is the printer status register. So what kind of I/O technique is this? Is this memory mapped I/O or I/O port space? This is a real code. This is real C code that does the programmed I/O. And obviously I am modifying some registers in my printer controller. The question is, which one am I doing? Which one? Let me go to this picture. Am I doing this or that? The first one, A, separate I/O and memory space.
You're modifying the register directly, so I assume.
Okay, let's go to, what was it? 30, right? How would you do that? I mean, how would you do? Remember, for the separate I/O space and the memory space, it needs special instructions to write to. Am I using any special instructions? No. All I am saying is that this variable here is a pointer, right? Printer status register. Okay. So all I am doing is that it's a pointer. Let's say it's an integer pointer. Printer status register. I assign a value to it, 0 to be 75. Where did I get this address? Okay. Memory mapped I/O says that I am going to keep that register at this address, and I assign this address to this pointer, and in my C program I just dereference that pointer and see if that register contains the value of ready in there, right? So this is memory mapped I/O, definitely a memory mapped I/O. Okay. Another one is okay, another integer pointer is printer data register, and again it has some other address in it. So that's the advantage of using memory mapped I/O, right? Writing a C program like this is very similar to copying some data from one location to another location. So that's the advantage of having memory mapped I/O. Otherwise, again, in C I have other functions, other procedures that does the in and out. I forgot what was the for C. Are they part of the POSIX C language? I/O operation. functions. I am not connected to the internet. Maybe I should be. Let me see if I can find any examples of it. Am I connected? Okay, no, I think I need to look it up. These are regular input-output functions about the library I'm talking about. Well, I guess it's going to be the standard in and out assembly instructions of the language. So you need to make assembly. You need to switch the assembly to do those operations. Anyway, it's going to be complicated that way. This is much simpler. So it is polling. I am polling if the data if the printer is ready. Whenever it is ready, I put this character and I wait until the printer is ready again. Obviously, this is wasting lots of CPU time, and but it is very simple. It is very simple to write. Here we are not talking about the interrupts and that kind of stuff anyway. And you might say that who uses such a inefficient way of handling the input-output? Well, I mean, you are wasting the CPU time, right? Well, if you don't have a multi-programming computer system, if your operating system doesn't need more than one process running at the same time, well, this is a very logical, very convenient way of handling things, right? I mean, here I am wasting the CPU time. What am I going to do if I am not wasting the CPU time? If I don't have anything to do other than this procedure, right? Then the CPU time will be wasted anyway. So why don't I waste it here? At least I know what it is doing right now. Okay. So for very, very simple computers with just one task, okay, if I am not in a hurry, then that will be it. So this will eliminate completely the need for an interrupt controller, right? DMA chip, that kind of stuff, and multiprocessing, multitasking. They are all gone. Very simple stuff, and it will work. It will work this way. So this is called programmed I/O. Okay, programmed I/O. It takes CPU time. If each character takes 10 milliseconds to print, after every character is written to the printer's register, CPU sit idle loop for 10 milliseconds. So we are wasting those 10 milliseconds. And if that 10 milliseconds, if I am doing multi-programming, and if that 10 milliseconds is enough to do a context switch, 2 times the context switch to some other process, do some useful stuff. When the print is ready, come back to this procedure again, then that would be logical. Okay, so that means what? We need to make this decision. Is 10 milliseconds long enough to? 10 milliseconds long enough to? Is 10 milliseconds long enough to do a context switch and handle the other process and come back? That will be the decision. Usually, yeah, 10 milliseconds is a very long time for a computer to do context switch. And if this is the case, then we are going to do this. We will use the interrupts. Okay. So you are going to go to sleep. We are going to ask the operating system. Okay. I am going to be blocked until this is ready. Whenever it is ready, the printer will cause an interrupt. Okay. That interrupt will be handled, and this process will be unblocked. That's called the interrupts, and let's look at the same thing with the interrupts. Okay, the same exact thing. Okay, this process says that print this buffer to the printer. I got it in my kernel space, so this is in my buffer now. By the way, I am keeping the copy of the same thing 2 times. One is here and the other one is here. Okay. You might ask, why don't we, instead of copying this from here to there, okay, why don't we use the user's copy? Okay, so I don't have to make a copy of it, because these are the exact same copies of the same thing, right? Instead of copying it to my kernel space, why don't we use this one? We are going to look at these kind of problems later. Okay, let's look at this interrupt-driven I/O. Okay, like I did before, copy from user. Okay, I copied from user my buffer this many times. Interrupts are enabled. I am in kernel mode, remember. Okay, and first there is an infinite loop here. Wait for the printer to be ready. Okay. Whenever the printer is ready, before before I start doing anything, I need the printer to be available. Once the printer is ready, put your initial character, okay, P0 to the printer data register, and call the scheduler saying that, okay, I am blocked. Scheduler will schedule something. Scheduler will schedule something for you, something else. Okay. This part A is the code. It is executed at the time the print system call is made. So if somebody makes a system call to, okay, print this buffer for me, this is the part that will be printed. Okay. Part B is the interrupt service procedure for the printer. Okay. So whenever the printer becomes ready, printer calls an interrupt. My operating system takes care of the interrupt. It says that, okay, if my count is 0, then I have printed everything. So unblock the user. Otherwise, okay, put character number I into the printer data register. Okay, then decrement count by 1, increment counter index by 1, and acknowledge the interrupt saying that I handled the interrupt, and I return from the interrupt. Okay, so this is the interrupt handling routine. This is not part of the user's process. This is handled by the kernel automatically. So every time a printer interrupt happens, I handle it this way until this count becomes 0. When the count becomes 0, okay, when the count becomes 0, I unblock the user. So unblock user means that whoever made this call to print the data, it will be unblocked. Now we are saying that your data is printed. Okay, so this is interrupt-driven input-output. You might say that, well, we are wasting some time at this line to wait for the printer until it is ready. Well, I mean, again, we can use some other interrupt solution for that part, but just to keep the picture simple, we kind of ignored it. So this is not happening actually in real life. We have another interrupt procedure for that one. We are going to wait until the printer is ready. Okay, we are not going to wait in an infinite loop. Yes.
When does the interrupt service routine is called? After the scheduler function is being called, or the printer data register is being assigned?
You mean when does the interrupts are programmed to do this? Well, you see this enable interrupts. This enable interrupts means that if something happens about this printer, if that printer causes an interrupt, you are going to handle it this way, and this is how we have handled it.
I was asking this interrupt in this section B. There is an interrupt service procedure code. When does this code is actually called?
Whenever a printer issues an interrupt. Printer issues an interrupt, says that the print is ready. Okay?
So printer issues an interrupt after the data register is being assigned, or after calling the scheduler function?
Printer issues an interrupt when it prints a character.
When it prints a character.
Well, printer causes lots of interrupts. One of them is printer ready interrupt. The other one is, for example, printer needs attention interrupt. The other one is, for example, printer needs something else. But most of the time, it causes this interrupt. Printer is ready. Okay, any other questions? Okay, good. So again, this part of the kernel, part of the kernel. As an end user, all I am doing is that, okay, send this buffer to the printer, and I am blocked. And this is where I am unblocked. This is called interrupt-driven input output. Okay, so obviously the disadvantage of this interrupt-driven I/O is that an interrupt occurs on every character, and you might say that, well, this is very simple to handle the interrupt, but again, this interrupt handling routine is run after I handled all those interrupt related stuff, saving all the CPU states, okay, doing all the context switching steps. After that, this one is handled, and basically it is context switching 2 times, and it is costly actually. Okay, so interrupts take time, so the scheme wasted a certain amount of CPU time. And remember this one, what did it say? A programmed I/O, remember I am waiting for printer to be ready. Let's say if I am waiting for 10 milliseconds, if 10 milliseconds is enough for me to do context switch 2 times, okay, if you consider all those kind of cache invalidation, updating of your memory map tables and etc., then you can do the interrupt-driven I/O. But again, interrupt-driven I/O doesn't mean that for every character I am just running this loop, this simple code. This simple code is at the center, but before coming to this one, there will be lots of other overhead. Okay, so interrupts takes lots of time to handle. So the other logical solution is, if you have the DMA chip, solution is to use the DMA. Okay, so DMA is very similar to programmed I/O, right? It will be very similar to programmed I/O. Instead of CPU executing these lines, DMA chip executes them. You may view it that way. Okay, DMA chip knows, okay, where the data is. DMA chips knows how to transfer data between the memory and the controller devices. And if we program the DMA chip for us, then we can do the DMA based input output. Okay, so it's a special hardware DMA controller. Again, it's a controller. We have the hard disk controller, SSD controller, printer controller, interrupt controller, and a DMA controller. It is on top of it sits on the bus, okay, system bus, like the memory or the other devices, and it can be programmed using its own special registers. Okay, so DMA strategy requires special hardware, but using this special hardware, I can free up the CPU during the I/O. Even if I have the interrupt capabilities, interrupts take time, but using the DMA is going to free us from all that. Okay, so DMA controller feeds the characters to the printer one at a time, without CPU being bothered at all, even without the interrupts. Okay, so in essence, like I said before, DMA is kind of a interrupt-driven input-output. Okay, interrupt is like a programmed. DMA is kind of programmed output, only with the DMA controller doing all the work instead of CPU. So DMA is like a very, very, very simple, stupid CPU. All it does is just copy stuff between the controller's buffers to the memory and the other way. Okay. Okay, so the DMA is saving us from interrupts and waiting. So part A, code executed when the print system made its call. Okay, when the user says that print this for me, I copy data from the user space to my space. I set up my DMA controller and I block myself. Okay, that's it. And whenever the interrupt happens, okay, whenever the interrupt happens, what do you mean? Who causes the interrupt now? It says that the interrupt service procedure. This is how I handle the interrupt. Acknowledge the interrupt, unblock the user, return from interrupt. Who is causing this interrupt? Remember, I am printing some data to the printer. Previously, this interrupt is caused by the printer because printer says that I am ready. How about now?
Control.
What controller?
DMA.
DMA controller, exactly. DMA control, who said that? Okay, good. DMA controller says that I did whatever you told me. I copied all that data to the printer's controllers by checking if the printer is available. Everything is printed now, okay? So CPU just handles this interrupt. So the total number of interrupts handled is just one. And I set up my DMA controller and that's it. So using this DMA controller, the input-output is very convenient. It is both efficient and easy too. But the downside is you need the DMA chip, DMA controller. And if all the processes are doing the same thing, instead of doing their I/O using their CPU time, they are programming the DMA controller. So that means that I need the DMA chip for many processes at the same time. So maybe you should have many DMA chips available, or the same DMA chip can service many processes at the same time, and that's what we are doing actually with the modern operating systems.
Sure.
Yes.
Why are we calling scheduler after the DMA?
Remember, this is our kernel. Okay. So somebody said that print this buffer for me. I copied this buffer, I set up the DMA to print it, and then I am calling the scheduler so that it can schedule some other task to use the CPU, because this current task cannot continue until this is done. Okay, so this is in a way that blocking the system calling process. And we did the same thing here too. Scheduler. Remember, this one doesn't use any schedulers. Okay, when the user makes a system call, print this buffer for me. Okay, kernel is busy either printing the data or waiting for printer to be available. So kernel will be a very inefficient kernel. Nobody else can use the CPU. That's why we didn't like it. In this case, we block the calling process. Similarly, we block the calling process. This one is way more efficient because this printing process will not use any CPU time until the whole thing is done. This one, for every character printed, this one will be using the CPU time. Of course, this is a very simplistic picture. No printers work this way for the last 40 years. Okay, because printers are smart enough to get the whole page and print it out. Okay, you just copy the whole page to the printer's controller's buffer, and you say that you go ahead, you print it. Okay, the printers are actually very capable computers. They have megabytes of buffer available, and they have their own interfaces, right? And some of them are directly connected to the Wi-Fi network, and they are computers. But again, this is a very simple picture to tell you how the interrupt-driven and programmed I/O works. Okay, good. Any questions so far? We are still looking at the software aspects of the input-output part of the operating system. Okay, so if we like to categorize the input-output software, these are the categories, maybe I should say the layers of the input-output software. At the bottom we have the hardware. On top of it we have interrupt handlers. Remember the interrupt handlers? Whenever an I/O device says that I need attention, okay, somebody has to handle it. What kind of attention? Printer says that I am ready. Printer says that I am I need attention. I am out of ink. I am out of papers, etc. the hard disk says that the data is ready, or hard disk says that I am ready, etc. So these are the interrupt handlers. On top of it, we have the device drivers. Device drivers are the part of the operating system, that knows how the controllers work. Okay, these are the ones that know the special registers of that I/O device. Okay, remember the controllers? Controllers are the special electronic circuits that communicate between your computer, that provide the communication between your computer and the device itself. The device drivers are the part of the software components of the operating system that does this communication. So they know a lot about the devices. But on top of it, we like to make everything independent of the devices that we are using. So device independent operating system software. Your new homework, your new file system, you are going to write it in C code, okay? And it will do inode based file system operations, like the making directories, removing directories, and etc. Okay, and you are going to write it in C. It would be very easy to port your whatever you are writing to a specialized device. Okay, most of the logic is complicated, yes, I know that, but just to make it dependent on some kind of a special device is not a big problem. So you are writing a file system, that will be most of the time independent of your devices. And on top of it, you have the user level I/O software, okay, like your file operations, open file, create file, delete file, and etc. Okay, so we are going to look at these. We looked at the interrupt handlers a little bit. We are going to look at this device drivers a little bit, but it looks like maybe I am out of time for today. Yeah. Are there any questions? Yes.
What do you mean that we would need for the homework? I didn't understand.
What do I mean? What?
For the homework, you said something that we would need to somehow focus on one device to execute it.
No. Well, for the homework, you are not going to devise any. You are not going to. For the homework, you are not thinking about any devices, right? Where am I keeping this? Where am I keeping this data? On a disk, on a CD-ROM, on USB, and etc. Still, you are writing a file system. Okay. It would be very easy for you to port it to a specific device. Okay, because all you need to do is, where am I going to keep all these inodes? Instead of reading the blocks of memory, I should read this from the hard disk or SSD device. Once you make those modifications, your whole file system will work on any kind of device. That's what I'm saying. Okay, so what you are writing is not device independent. Yes, it is dependent, but making it independent is going to be easy. Okay, any questions? Okay, that's it for today. On Monday, we have a guest speaker, Mustafa Chamorlu. He is one of our graduates. He will be talking about virtualization, but I don't think that I will be done about this I/O by Monday, but he will talk about the virtualization anyway. So on Monday we have a guest speaker, and I will be taking our regular attendance on Monday too. Okay, I'll see you tomorrow.